Here is a metal air screw on test. It is the latest development of a design which has been in worldwide use for several years. Air screws are designed for a certain engine power. To make sure that the calculations of the designers are correct, new types must be tested under working conditions. When these tests have been proved, the air screw is put into production. Roughly shaped parts and raw materials come into the factory for machining. Each new batch must be tested to find out whether the qualities of the materials come up to specification, whether each metal used is strong enough for the job it has to do. These are test pieces of a light aluminium alloy called duralumin, used to make the air screw blades. The structure of the alloy is examined through a special microscope. It shows whether the material has been correctly treated during the many processes it has gone through before arriving at the factory. This magnification of the surface shows whether the different metals are evenly mixed throughout the alloy. Here they are separated into groups. This is a bad example. A good alloy has an even structure like this. Forged metal, like wood, has grain. Unless this grain is made to flow in the right direction, the metal part will be weakened. The grain flow can be seen by etching the surface of a test piece in acid. In this section, the grain flows with the shape of the blade, bending round with the curve of the shoulder. This means that the blade has been correctly forged. One of the most important routine tests is to find out a metal's exact tensile strength. The tensile strength is the force needed to break it by stretching. Some metals, such as mild steel, can be seen to stretch quite a lot before breaking. Up to a certain point called the elastic limit, when the load is removed, the metal will contract again to its normal length. If stretched beyond the elastic limit, it stays pulled out and is often weakened. This test is to make sure that the work an air screw part has to do will not overstress the metal. The duralumin blade comes into the factory as a forging. It has been pressed or hammered out from a heated billet of metal. The blade is first rough machined to give it its basic shape. A master, shaped like a blade, guides the cutting edges of these machines. For this reason, they are called profilers. From now on, the blade is hand-shaped by skilled craftsmen. This is done on a special table marked out in equal divisions called checking stations. These stations are marked onto the blade so that a regular check can be kept on size and shape. Surplus metal is taken off the blade by a coarse grinder. Straight edges show up at once any overworking in one place. Each stage in the making of every air screw part is checked by inspectors to make sure that the blade conforms to its design. Templates, a different one for each checking station of the blade, not only guide the worker, but show the inspector that the work has been done accurately. When it has passed this inspection, the blade comes into the fine grinding section. At this stage, so little metal is left to remove that a fraction too much off in one place would upset the balance. So the worker tests the balance of the blade from time to time against a master weight. Inspectors then test once more for balance. All angles and measurements are checked and noted on the record which follows each blade right through the factory. Many different sized blades are made, from the large air screw for airliners and bombers to the small air screw for two-seater training machines. A polished air screw is exposed to the action of the atmosphere. It may also catch the sun and dazzle the pilot. So today, most blades are treated to preserve the surface and to prevent dazzle. First of all, the polished blade is shot blasted. Very fine steel shot is blown onto it, which dulls the surface. So fine is the steel shot that the worker must wear special clothes and a respirator to protect his lungs. The shot blasting prepares the blade for special electrochemical treatment. This treatment has two objects. It hardens the surface, and it shows up instantly any surface flaw in the metal. After this, most blades are dyed to prevent dazzle. Dye is used because it penetrates into the metal and is not so easily scratched off as paint. Now that we have seen how carefully an air screw blade is made, let us see the reasons for its special shape. Each blade of an air screw slicing through the air thrusts the aeroplane forward in much the same way as a ship's propeller cuts through water. The distance the aeroplane travels forward at each revolution of the air screw depends largely on the angle at which the blades strike the air. Broadly speaking, blades with a large angle will move the aeroplane further than those with a small angle, provided the air screw is turning at the same speed. The tip of the blade has a greater distance to travel than the root. The tip, therefore, moves faster than the root. If the blade were the same angle all along its length, the tip, because it is moving faster, would tend to drive further forward than the root. So the blade is shaped with a smaller angle at the tip than at the root. The average angle along the blade is called the pitch angle. Now, whenever an aeroplane flies, it must take off from the ground and it has to climb. Then it cruises at some level above the earth. The ideal way to meet these different conditions is by altering the pitch of each blade. Small pitch angle, like low gear on a motor car, helps an aeroplane to take off quickly and to climb well. But for cruising, a large pitch angle or high gear is more efficient. With a modern airscrew, the pitch of the blades can be automatically adjusted in flight to meet varying conditions, and the engine can be kept turning steadily at its most efficient speed. This kind of airscrew is called constant speed. These parts make up one constant speed airscrew. They are fitted together on a special shaft which is the same size and shape as the engine shaft. The barrel or body of the airscrew is in two halves. The back half goes on first. Inside the barrel is the spider. This is fixed to the engine shaft and is the means by which the engine turns the airscrew. The spider must sit firmly in the right position from the beginning of the assembly, because all the parts are fitted together on it. So it is fixed by a nut. These blocks keep both halves of the barrel in position. The front half of the barrel is then put on. The complete barrel holds the airscrew together, keeping the blades from flying outwards under centrifugal force. At every stage, the airscrews are examined. This test is to make sure that the blades are not held so tightly that the airscrew would jam, nor so loosely that it would vibrate. The inspector notes the number of the blade and the stage in the assembly. Blades may be 7 or 8 feet long, yet the tip of each blade must pass within 1/8 of an inch of the same point. The mechanism for altering the pitch of the blades is inside this dome, which is fixed to the front half of the barrel. The basis of the working part is in two pieces, called cams. One cam is fixed to the hub of the airscrew. A piston turns the free cam by means of rollers running in slots. The The mechanism works on the principle of a piston connected to these rollers by a rod. The piston works inside the dome, which is filled with oil. Oil forced at high pressure onto the back of the piston pushes it forward and turns the free cam. By reversing the pressure, oil is forced onto the front surface of the piston, which is then pushed back to its normal position. The root of each blade has gear teeth, which mesh with the teeth on the free cam. In this way, the blades can be turned. This alters their pitch angle. In practice, the different parts are arranged more compactly than in this diagram. The dome is fixed to the front of the barrel. The piston is shaped to fit over the two cams inside the dome. The oil pressure which works the mechanism is automatically controlled by the engine speed. If the engine tends to run fast, the blades turn to a coarser pitch. If the engine tends to run slow, the blades turn to finer pitch. In this latest design of constant speed airscrew, the blades can be turned so far that the leading edges face the way the aeroplane is flying. This is called feathering. It is a great advantage to be able to do this, because in the unlikely event of an engine breaking down, feathering the airscrew will stop it windmilling. That is, being turned by the force of the air, which may damage the engine and causes drag. Finally, the complete airscrew is balanced in a special pit. This airscrew, which is the largest size made, will be fitted to an engine developing over 2,500 horsepower. This means that the airscrew will thrust into the air with the power of at least 25 motor buses. The airscrew is balanced in 6 different positions. Any slight bias is corrected by fixing lead wool, equal to these master weights, in the hollow bolts. The final balance is so perfect that a visiting card weighing less than a cigarette easily turns the whole airscrew, weighing about 650 pounds, as much as 5 men. Before the airscrew is sent out to the factory, it must be passed for balance, not only by the factory, but by the government inspectors. No airscrew leaves the factory without this official signature.